basically a bias containing a single function, containing just the average value, just the average function is inside this bias. So every time you guys decide to change the parameters of your learning algorithm, it doesn't matter, could be any algorithm, you are changing the bias. You are modifying those biases. So every time you try to get something more complex or something more simple, you are doing that by changing parameters or by defining topologies. For example, if you study deep learning does something quite close to this. It's going to increase the bias. And that's a problem. That's why we need to have like lots of training examples to be sure that something is being learned out of that very complex technique. If we have a simple technique, it's easier to ensure that because we don't need that many examples while training. That's quite interesting. And just to show you something, if sigma is very, very large in terms of this input dimension, you guys remember that this is the input dimension, this is the output dimension of our identity function. So every time we have a very large sigma, like infinite, we're gonna have like a single Gaussian function that's gonna be across the space defined by the x variable. And that's gonna bring like a single function. That's why we have a very small, a very restrictive bias containing a single Gaussian function. Instead of that, if we have like a very, very large space of admissible functions, we're gonna have very small Gaussian functions, one very close, infinitely close to the other. That's a scenario when we have like a sigma that tends to zero. That's very, very, very small. That's close to zero, like 0.001, 0.0002, for example. That's going to build up several functions like that, one to define each query point. So if you have a query point here, that's going to be its function. If you have a query point here, that's going to be its impulse function. So functions are going to be like impulses along this input axis and very, very close to each other. And that's going to bring an infinite space of functions from which we don't have that many learning bounds, that many guarantees that we are indeed learning. And that's a real problem. Guys, this is like the first talk just to give you like a rough idea about what I've been working with. I suggest you to study this book by Vapanik, this paper by Luxburg and Shokopf, and also this book by Shokopf and Smola. You guys can get back to the group and watch the video again. And I also would like to let you know that we have just published this book, which is called Machine Learning, a Practical Approach on the Statistical Learning Theory. Okay, and that book brings like new stuff, like how you could prove you are learning. And it's not just by chance. For example, some people, as I told you guys, like lots of people nowadays run deep learning strategies and they don't know what's happening. They run it. Run them, like lots of techniques, as if they were just black boxes. And that's not the purpose of machine learning. I mean, if you don't know what's happening, there's no reason to do it. You're just guessing. You are not a scientist. You are not like a machine learning scientist or a data scientist. You are just running strategies. That's what I've been doing probably, or most people. Yeah. So the main idea with this talk today is to define that we can indeed define parameters in some ways that we ensure learning. And that could be for any sort of technique, especially the supervised techniques. Techniques driven to tackle supervised learning. For example, if we are using like multi-layer perceptron or convolutional neural networks or like TensorFlow or Caffe or whatever, ResNet, things like that, we can indeed prove, for example, that the number of examples we should have to ensure learning. And that comes from this theory. I can discuss about that maybe in the next talk if you guys are interested. I don't know, because I just looking here, just 4 people now, and maybe it's gonna be 0 at 5 now, okay? Maybe 0 in seconds, because I know this is a little tough. It's a tough subject, but that's the point. It's tough, but if you know it, you're gonna drive like your decisions. You're gonna boost your decisions in some ways that you can't imagine. They're gonna bring like successful results, and not just by chance. It's also interesting to mention that every time you guys are using like k-fold cross-validation, leave one out, boosting, bagging, and those techniques, what you guys have been doing is basically using some sort of predefined technique to find a smaller space of dismissible functions where you can get stronger learning guarantees. But most of people don't know that. Just use it, but never. Oh, that's good. Oh, this technique is good. It provides like good results. For example, in Kaggle, we've seen like lots of people using XGBoost. But why? Basically because we are building up like as tight this space of dismissible functions to have like stronger learning guarantees. And people use it, but don't know what's happening there, what's happening behind. Of course, my idea is to study that like deeply and have like all the mathematics behind. I know you guys are probably not that interested in mathematics. Probably, I don't know, maybe you are. But even if you are not, you should know what's happening behind. And that machine learning, data science, and some people now say big data or whatever, or artificial intelligence is not just by chance. It's not like run and let's see what happens later, what happens next. Remember, we have something very important behind all this theory, which is the generalization. Generalization tells us I want to have a classifier that behaves in the same way in my sample as it's gonna behave in future data that I'm gonna receive in future. If I have that situation, I know I have a nice estimator, and that estimative is gonna be a good estimative for real world purposes. It tells me how my solution behaves for unknown data. If I have that, I can tell people that my decision is not by chance. That result is a result with a theoretical foundation. Guys, that's all for today. We still have like 6 minutes. I don't know if you guys have some questions. You can type here, and I'm gonna try to answer. No question? Maybe there is some delay here, I don't know. We still have 6 people around. That's very nice. Nice to know. At least I'm not like alone here presenting to myself. But I know this subject is a little dense. Where do you use it? Hardy, thanks for the question. I'm gonna say everywhere. If you have any sort of data science problem, you're gonna use it. This theoretical foundation is necessary. It's gonna bring the real meaning for the results. Okay, the distance weighted nearest neighbors. Okay, the distance weighted nearest neighbors. It's basically used for regression. So every time I have to perform regressions, like I work a lot with time series prediction and data streaming prediction. And DWNN is quite simple, and I use it a lot. Okay, in business. Okay. Okay. Could be like, for example, in my case, I use it for climate prediction. I've been using it to predict some, for example, there was this variable that defines the cultivable areas in Africa, which is related to temperature, pressure, and whatever, and the Sahel area. And in that, with that particular variable, we're capable of predicting how Sahel is going to behave and where people should grow stuff along the next 6 months. For example, we've been doing that with people from Max Planck, from other institutes too. That's quite interesting. That's academic, but it's interesting. There's another problem. I've been working with some people in practice. Like I already worked with some guys in Brazil to classify, not just classify, but to identify cover songs. And those cover songs require that same sort of knowledge. And DWNN is also an algorithm to use for that, to perform a regression in that scenario too. But it could be like any sort of regression scenario. You could mention like, okay, let's use it to tackle like time series like in the stock market. Yeah, you can do it. You can do it for stock market too. I've done before, some time ago. Let's see. Do you see an advantage in comparison with linear logistic regression? Okay, now comes like a very nice question. Actually, the only point about the algorithm is what that particular algorithm provides to us in terms of changing its bias, changing its space of admissible functions. For example, I'm gonna define something very simple. With DWNN, we are using Gaussian functions, right? Gaussian functions can be used, like the mixture of Gaussian functions can be used to represent any sort of behavior. Could be anything. So is it possible to use Gaussian functions to represent like something very complex using the mixture of Gaussian functions? Yes, it is. But that depends on the space you have. So for example, if I have a nice space of functions, that's going to be very interesting. I don't know if you guys have like some time, but I can show something if you are interested. For example, let me show something here. Okay. Maybe this is interesting for you. For example, guys, let's see what happens if we have like, okay, I'm gonna use something that's very interesting. I'm gonna open here and I'm gonna search. Let me see. This is a data set, which in my opinion is a very interesting data set. Let me see. Yeah, it's this one. This data set is very interesting. It's about, let me get out of this. I'm gonna download it. Okay. It's a data set that provides some climate information. Okay, in a bank. Okay, that's good. But I'm gonna show something very interesting at the beginning. I think you guys are gonna like this. Just take a look at this. I'm sure you're gonna love it. I'm gonna load this data set, which is basically a time series. Let's load it. It's in here, lorem 63. This LAR63, it's a data set with measurements of